some error here, so I was asking Vishal. Okay, it's
Okay, you're talking with Vishal. Oh, okay.
on live. Cool. I think it's live, right? Please check no. Um, Bro, Vinay,
Yeah, bro, now it is live.
it's live, right?
Yeah.
Okay, cool, bro. Thanks. Okay. So, okay. Anyway, we will be discussing a few problems today and informing students via WhatsApp. Last 12th. Hi, Shashwita. ಶಾಶ್ವಿತಾ ನಿಮ್ಗೊಂದು ಹೇಳ್ಬೇಕಿತ್ತು. ಇದು ನಿಮ್ಮ ಅಟೆಂಡೆನ್ಸ್ ಕೌಂಟ್ ಆಗ್ತಿಲ್ಲಮ್ಮ, ಚೇಂಜ್ ಮಾಡ್ಕೊಂಡ್ರಾ? Hi guys, good evening. Good afternoon. Afternoon alva. Good afternoon. Hi guys, hello everyone. Good afternoon. So hope everyone is doing great. Yeah. ಹೇಗಿದ್ದೀರಾ? ಏನ್ ಮಾಡ್ತಿದ್ದೀರಾ ಎಲ್ಲರೂ? ಆರಾಮ? So now we'll start our class today by 3 p.m. exactly. Okay, I hope everyone try to solve the questions which we had sent you. I mean, in your notes are open ಮಾಡಿ ನೋಡಿದ್ರಾ? questions solve ಮಾಡಿದ್ರಾ? ಇದು ಏನಾಗ್ತಿದೆ? Okay guys, hi everyone. So it's 3 p.m. and we could start our class. So hope everyone try to solve your questions. I mean, try to solve the questions of which were sent to you in the notes. So there were hardly 3 questions, I guess. Isn't it? Good afternoon all. Thank you, bro. Guys, so everyone, yes. Hi, good afternoon, Shashwita. Guys, for the Zoom people first, it's a very important message that your attendance are not getting tracked. I mean, you guys are attending the class, it's been recorded, the names are recorded, but we consider only the attendance when you share. I mean, when we collect the data from your Gmail ID. So whatever the respective Gmail ID you have given, we would cross check that for attendance. Please update if anyone is using some different ID for Zoom other than what you have shared to us. Please try to update us or try to change your Zoom ID with whatever you have given us. Okay, cool guys, thank you. Hi, good afternoon YouTubers. So good afternoon everyone. So hope you guys had a very great day today. So what's happening at your end? In our end, yes, we have pleasant weather here in Jainvi Hassan. So it's going cool. ಲೈಟ್ ಆಗಿ ಮಳೆ ಬೇರೆ ಬರ್ತಿದೆ. So what's happening at your end, guys? So hi. So quickly we'll start our class. Okay. Okay. Yep. So guys, how many of you tried this question? How many of you tried this question? Very first thing. So we'll start with the question solving. So we had 4 questions pending from previous topic, that is electric potential. So once we complete those 4 questions, we'll be starting with, we'll have a quick summary. Then we'll start with the next concept, that is electric dipole. So we'll be starting with electric dipoles today. So we have contents like electric dipole, electric field due to dipole, and what are different types of dipoles available. So we will try to solve few questions based on what we learned today also. So first thing, how many of you tried to solve this question? Please click on S. And how many of you got? How many of you tried and got? Please click on S. Yes, correct, Shashwita. Correct, Tejas. Yes, awesome, guys. So YouTubers, any answers? Please, guys. Yes. Hi. Good afternoon. Hari Prasad. Hi. So, hi guys at YouTube. Please respond if you have solved this question. So I hope guys, even you guys are able to access our notes folder. So I had shared that in our playlist description. Please go through that if you have not yet shared. If you are not got notes. Yes, Mega, check your answer. No. So guys, I hope everyone tried to solve this. So today we'll just quickly, I'm going to end this poll of technical check. I hope everyone is able to hear my voice clearly and my blackboard is visible clearly, right? Cool. So guys, yes, correct, Hari Prasad. Cool, awesome. So I'm going to launch the quick MCQ, answer poll, so that whoever answered, whoever tried this question could answer. Okay. You guys answer this question. Meanwhile, we'll get ready. So if anyone have not got the answer, we'll solve this. Okay. Yes, cool guys. So yep, come on. So what's given here in this question? So it's given that there is, okay. Why my screen is visible to everyone, right? Just a confirmation. My screen is visible to everyone, right? Yes. Oh, correct, Bhargav. Super, awesome. Yes. So what's given in this case, guys? So some equipotential surfaces are shown in the figure. So the question, I'm reading the question. The equipotential surfaces are shown in the figure. What can you say about the magnitude and direction of the electric field for each of the cases? So there are several equipotential surfaces. Say I see here 1, 2, 3, 4 equipotential surfaces at a separation of 10 centimeters from each. The consecutive separation is 10 centimeters. Now what we had to do, we had to find what is the potential. What is the expression for potential, guys? So guys, which formula are we going to use here? Which formula are we going to use here? So guys, tell me one thing. So from here to here, sorry, this point, okay? Exactly to this point, what's the distance? From here to here, what's the distance? Guys, you should be very active today. Please try to respond. Yeah, though the question seems silly, it's not silly. Please try to answer. Okay, what's the distance from here to here, guys? 10 centimeters, right? It's 10 centimeters. Correct, guys. So what's the distance from here to here then? What's the distance from this point to this point? In this case, only if we had a number line, what's the distance? Yeah, it's still 10, right? 10 centimeters only, sir. Okay, what should we do? So while considering the equipotential surface, is my distance same? Is my distance going to remain the same? When my equipotential surface is at 30 degrees, is my distance between them remain the same? Yes, Madhavi, cool, superb. So we're going to use that formula, exactly, yes. So E is equals to, okay. So the formulas which okay, I'll write down what are the formulas which we are going to use today. So we'll be going to use E is equals to minus dV by dr. So what is this? Which formula is this, guys? Or say, since this is a big change, I'm going to change this formula as delta V by D. I'll take this as delta V by D. Okay, minus delta V by D. Let's take E is equals to delta V by D. Okay. Yes. Okay, cool. So guys, yeah, coming back to this question, so we'll be using this. So yeah, now tell me quickly, tell me guys, what is the distance between these two? Okay, I'm changing my color for black. I mean white background, I should change the color to red. So you guys say this is 10 centimeters again, but guys, distance between, so this is the distance between 2 points, right? From 10 to 20, it's 10 centimeters. Now tell me, what's the distance between two equipotential surfaces? So what is distance or displacement or whatever you want to say? What is the length between two equipotential surfaces? Effective net potential. I mean, what is the net distance? What is the net distance between two equipotential surfaces? Is it still 10? Yes, correct. Potential. Yes, Madhavi. Correct. So, Madhavi, I hope you guys know about gradient by now. I mean, guys, did you study gradient in maths? Is gradient in maths? I mean, do you have gradient and divergence and curl in your maths? I don't know. I feel that's in your degree level, right? Okay, so those, okay, it's not there. Okay, cool. Uh, Good, Madhavi, you have used. Yep. Yes. So, Hari Prasad, no, check your answer. So, guys, what is the effective distance between two equipotential surfaces? Yes, yeah, what's it? Tejas, yes, what's the magnitude of distance between two equipotential surfaces? So, if you consider the parallel distance, what could it be? So I literally mean I want to convert this angle to, or this slightly slanted lines to straight lines. What should we do there? So guys, the distance between equipotential surfaces which are parallel is given by, okay, net distance is given by 10 sine 30. Okay. So why are we doing 10 sine 30? Tell me why are we doing 10 sine 30, guys? When these are slanted, we don't get the exact distance between these 2 points. So though the distance between these 2 points may be 10 centimeters, but when they are vertical lines, we studied equipotential surfaces as vertical lines, not as a slanted lines. So when we try to convert them, so we have to consider the distance between two consecutive equipotential surface. Say if this is 10 volts, 20 volts, 30 volts, and 40 volts, the distance between these should be considered when their angle is 90-degree. Okay. If so, then what's the effective distance between these two? So it should be 10 sine 30-degree, guys. Should be 10 sine 30-degree. So what's that? D is equals to 5 centimeters in that case. Okay. So consider D is equals to 5 centimeters and try to solve for E. E is equals to delta V by D. So we're just calculating the magnitude, not the sign. So sign is not important. So try to solve this, guys. Delta V by D. What is delta V? Change in potential. Say what is change in potential, guys? V final, potential at final minus potential at initial. Right. Divided by distance D. So we found the effective distance between two consecutive equipotential surfaces as 5 centimeters now. Okay, try to substitute everything, guys. Say if I take any two consecutive equipotential surface, say first two, then it would be 20 minus 10 by 5 centimeters. So into 10 power minus 2. So try to solve this. What's the answer I get? What's the answer I get? So guys, how many did not understand why did I take the distance as 5 centimeters? I know most of you are keeping quiet. That means I feel that why? I mean, yes, correct, Sakshat Rai. Your answer is correct. So, guys, tell me why did I take 5 centimeters, or why is the net distance 5 centimeters instead of 10 centimeters? So, since you guys are not asking me the question, I'm asking you the question. Guys, please be active. Please respond. Did you guys get why we took distance as 10 sine 30? That's my question. If you have got, then why? If even one answers, yes. Yes, correct, Dhanush. Superb. Awesome. So should I consider you have understood this? Yes, correct. Correct, Tejas. Superb. Guys, please respond. There are 25 plus participants in this Zoom class, and there are many participants in YouTube. Please try to respond. Have you got this? The point is, see, yes, the slanted positions should not be taken. We should consider only the vertical position. So we are converting this 10 cos 30 or 10, we are taking the distance as 10 sine 30 degrees. So yeah, we should consider perpendicular distance. Yes, correct, Lakshmi. Correct. So V final minus V initial. This was the formula for electric field. Yes. So yeah, exactly, Hari Prasad. So we have to consider E is equals to delta V by D. That is V final minus V initial by the separation distance in vertical condition is 5 centimeters. We have substituted it. So we got 200 volts per meter, right? So if this is the electric field, this is the expression for electric field. What else was asked there, guys? So they have asked one more. What is the magnitude? They have asked what's the magnitude and direction of the electric field. So you guys found the magnitude, right? So you guys found the magnitude. Magnitude of electric field is 200 volts per meter. Now what about direction? What about direction? So how to find direction, guys? In the direction of electric field. So we should consider the angle made by the uh, e- electric field with positive x-axis and add 90 to that. Okay. Yes, correct. Tejas. Cool. Superb. Yeah, you awesome. So yeah, guys. So how to find the direction is the direction as they just have said. So direction of electric field is electric field should be perpendicular to direction of potential, right? Guys, how many of you remember this? Click on S. So if you remember, while we were studying electric potential or equipotential surfaces, we considered electric field, uniform electric field. In which direction did we consider the equipotential surface? In which direction did we consider the equipotential surface? So if I want to find the equipotential surface along the electric field, in which direction, in which angle should I move? Please reply yes. Correct, Dhanush. You should move in perpendicular direction. So yeah, when we move in correct, Sashvita. Superb. Thanks for the reply. So when we move in the perpendicular direction, we got the electric field. Or when we see if we have given the electric potential, now if we move in the perpendicular direction, we get the electric field, right? Perpendicular to electric potential will be my electric field, and vice versa. So we got that electric field is perpendicular to the direction of electric field is perpendicular to the direction of potential. Now my initial electric field direction with respect to x-axis, electric field angle with respect to x-axis or horizontal is ಎಷ್ಟು 30 degree was 30 degree. Now what is the effective direction direction of electric field? 30 plus 90 agata. It's 30 degree plus 90 degree, right? Yes, that is 120 degrees. Yes, correct, Devikaran. Cool, awesome, thank you. So yes, guys. So answer is option D. Option D is your correct answer. Hope everyone have understood this. Please click on yes if you have understood this. So guys, let's solve these questions fast, and we'll go to the next topic also. So I need your help, guys. If you guys respond quickly, I can go quickly. Alva? Yes. ನಿಮ್ಗೆ I don't know about others, but most of you know this. Okay. So okay, this is only for the Karnataka students. So others don't worry. Okay, cool. ಒಗ್ಗಟ್ಟಿನಲ್ಲಿ ಬಲವಿದೆ ಮುಂದೆ ಸಾಗೋಣ ಬನ್ನಿ. So guys, I hope everyone try to solve this. So yeah, please respond me. So I have given this as homework to you guys. Respond me, what is the answer you get? So this is a kind of derivation. So so it's the same case. So there is some electric field given. So there is some potential given. So you have to predict what's the direction of electric field and what's the magnitude of electric field. Hope you guys have tried this. Cool, cool. Thank you. Thank you, guys. Thanks for responding. So guys, try to solve this question. If you guys have already solved, reply in the chat box. So what's your answer? So what's happening in this case, guys? What's happening in this case? Yes, what's happening in this case? So the thing is, what's happening here is, so here, okay, first tell me, in which direction is my electric field, guys? If you guys remember, in which direction should my electric field be? What is the direction of electric field? So if I have some random electric field here, say, what can I say the potential at this end? Guys, tell me. What can I say the potential at this end, left hand? V, high or low? High or low? What's the potential at the left hand, guys? Higher potential or lower potential? Reply, please. High. Yes, this is high. So this should be low then. So yes, yes, correct, Danush. So now, if you guys remember this, then tell me in which direction is the electric field for this particular diagram. So is it from inwards to outwards or outwards to inwards, guys? The electric field is from inwards to outwards or outwards to inwards? See, what was the condition, guys? My electric field is, yes, correct, Tejas, awesome. So others, Prakash Koda, check, correct, Namrata. So we know that, yes, correct, Ramakrishna, thanks, Bhargava, correct, Devikarani. Yes, correct, Prajwal. So yeah, we have this equipotential surfaces. It's the spherical equipotential surface which we had discussed the other day. So where is my electric field coming out, coming, guys? If you remember, even the spherical equipotential surfaces, you could say the 3D diagram which I showed you the other day, you could say from there, where is my electric field coming from or going to? Yes, most of you have answered here, guys. Thank you. So my electric field is coming from inwards to outwards. See, as I go inwards, my electric potential is increasing. As I go outwards, my electric potential is decreasing. So my electric field will be always in the direction from higher potential to lower potential, right? So my electric field will be going from inwards to outwards. Okay, it's in the outward direction. Now, what is the magnitude of electric field, guys? Tell me. Consider this is V1. Yes, correct, Likita, correct. Hariprasad, check your answer. Correct, Bhargav. Correct, Madhavi. So guys, consider this is V1, this is V2, and this is V3. V1, V2, and V3. Now, if these are V1, V2, and V3, can you find something general in this, guys? Can you find something general in this? Say, can you arrange this in descending order? So we have to arrange this in descending order. So first I'll get 60V greater than 30V greater than 20V. So this is the order which it's passing, or V3 is greater than V2 is greater than V1. Okay, so if I call this, then my V1 will be equals to 20 volts, my V2 will be 30 volts, and my V3 is 60 volts. So if we take the potential, so guys, what is general in this? What is general in this? Dhanush, okay, we'll try to simplify this as much as possible. Okay, we'll try to take a mathematical function here. So guys, if you see my guys, do you know what is this Okay, if you see what is common in these three, what is common in these three, what is the LCM of these three, guys? Can you find the LCM? So we'll go. I have a shortcut with that. So if we want to find this, I want to find the LCM. 60, correct, right? So if 60, if I want a single digit number, if I want, yeah, the LCM is 60. If I want a single digit number, can I divide all these three by 6? No, 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 I can't divide, right? Okay, if I multiply these three numbers with 6, can I get 20? No, I can't get 20. I can get 30 and I can get 60. So yeah, LCM is 60. Okay, yeah, right. Okay, guys, how many of you know this arithmetic progression? How many of you know arithmetic progression? What is the general formula for arithmetic progression? Yes. So we the arithmetic progression GP, sorry, not arithmetic, geometric progression GP will be a r power n. Guys, okay, correct, correct. Lakshmi, Bhargav, Wala, Raju. Okay, correct. So guys, I hope everyone knows this geometric progression. It's written in the form a r power n, right? So, so if we take potential variation, so can we take the potential variation 60? Okay, r power n, alva? 60, 30, and 20. So if I take their respective positions as, I mean, if I take the respective potential variation as V is equals to A into R power N. Can I take this way? Can I take this way? Electric potential, yes. Sorry, not AP, guys. I meant for GP, geometric progression. It was GP. So V is equals to A into R power N. Can I write in this form? Yes, please check. Guys, take some 30 seconds time and check. Can we write electric potentials in this form? Okay, R power n minus 1. So just okay. Guys, try to find the values in this form. Can you find? Can we find values in this form? Okay, R power n minus 1. Okay, sorry, sorry, guys. R power. Thank you. Thank you for correction, Tejas and Bhargav, Lakshmi. Cool. So, okay, can you find the values of A and N by substituting? I mean, can you find the values of A and N here for these geometric progression if it's in a geometric progression? Can you find the values of A and N? So we have V1 is 20 volts, V2 has 30 volts, and V3 has 60 volts. Now, if you take the potential variation as V is equal to A into R power n minus 1, here into R power n, then we can find, so guys, try to find these values of V and N. Okay, try to find the values of, sorry, A and N. A and N, small a, and N. So there is a small thing, it's not possible. Huh? Okay, guys. So let's discuss this problem again in next class. I'll give you a proper clarification to this in next class. There is some issue or error in somewhere, so we'll check that and we'll discuss. Okay, we'll go to next question. So, guys, try to solve this question. Okay, they are not in GP. Okay, fine. So discuss more. So, guys, try this question. No? That question I always had some doubt. I have to clarify that anyway. Yeah. So there are n drops. So what's given in this question is, we'll anyway solve that question sometime later. Okay, cool. Okay, thank you, guys. We'll check that. So we have n number of drops. Say I have n number of drops whose radius is small r. Okay, whose radius is small r, and each carries charge of small q. Okay, each have a radius of small r and each carry a charge of small q. Yes, Hari Prasad, we can check that. Okay, if that is done, it will take a lot of time to solve. So I tried to solve in a shortcut way, but that was not working. So I'll check that again and let you know. So guys, try to solve this question. So what we have is we have n number of small non-conducting drops of same size. Say they consider it's water. So these are n number of water. Now what's happening? They are of same size. Say all are having the radius of r. So it's spherical in nature. So when these tiny drops collides means they come to join. They come together. What happens? So when they come together, what happens? Guys, what happens? Tell me. Reply in the chat box. So each drops are having n, I mean q as their charge. So these n drops. So this is nth drop. So these n drops combine to form a bigger drop. Okay, they combine to form a bigger drop of radius capital R. So this is a question. Now find the potential. Say if each charge had a potential of V, if each small charge had a potential of V, what is the potential of bigger charge? V big. So this is the question. Guys, take 2 minutes time. Try to derive an expression for this, and yeah, we'll discuss about this. Okay, take some 1 or 2 minutes time and try to solve this. No. Yes, they repel. Yes, correct. They repel each other, but but so what's happening here, guys? So I'll tell you one thing. So what's happening? Uh, okay, I hope now. So what happening is, so each are of positive charge, right? Each is of positive charge. Now, yes, correct, Devikaran. They form a bigger charge. ಹೌದು. So each are having a positive charge, and now what happens? Yes, these positive charge repel, though though they repel, these drops come together because of some other external force. Assume it comes together and forms a bigger drop. Now what happens is all these drops, since they are positive in charge, so they try to repel away. They try to repel away. Now what will happen when they are trying to repel away? They only form. I mean these charges are stored only on the surface. Okay, these charges are stored only on the surface, not inside, only on the surface, and are staying away from each other. Yeah, they form a large drop, and these charges are on the surface, and they try to repel from each other on the surface only. So they spread out. They spread out on the surface. Now, what is the effective potential for this big charge? You have to find this. So this is the condition. Yes, one more hint is here. The hint is volume. Yes, is conserved. Consider the condition volume is conserved. So whatever the volume of the drops, it's not reducing. All the volume which is coming there is coming together to form a bigger drop. That's it. So volume is conserved. Try to solve this question, guys. So what is the volume of sphere, guys? What is the volume of the sphere? What's the volume of sphere? Come on, tell me, guys. Hello. Yes, come on, people. Reply fast. Volume, hey, volume of sphere, ಹೇಳ್ರಪ್ಪ. Yes, correct, Hari Prasad. Yep. So, yep. Volume of charges. Hari Prasad, check your answer. Whichever you gave is not the exact thing. Volume of sphere was, yes, 4 by 3 pi r cube. So this is the volume of small sphere, right? Yes, correct, Tejas. Correct. Exactly correct. ಅಷ್ಟೇ ಆನ್ಸರ್ ತೇಜಸ್ ಹೌದು. Yeah, correct Ramakrishna, correct Likita, Namrata, correct, Bhargav, correct. Awesome. So guys, see, volume is conserved. So these are the volume of small spheres. So small spheres volume italam. So that's the volume of these small spheres. Now, if the radius of this bigger sphere is capital R, what will be the volume of this bigger sphere? Well, big sphere will be, what will be the volume of big sphere? It will be 4 by 3 pi capital R cube, right? Now, what's the relation between this small volume of n small spheres and one big sphere? What's the relation between n small spheres and one big sphere, guys? Tell me. What's the relation between n small spheres and one big sphere? Yes. So from here we can say that 4 by 3 pi capital R cube will be equals to n times of 4 by 3 pi small r cube. Since my volume is conserved, yes, correct, Bhargav. Yes, Madhavi, correct. Dhanush, correct. Alvam. So from here, can you can you find radius, capital R? What is the radius of bigger sphere? Yes, Ramakrishna Reddy, correct. So what is the radius of bigger sphere from this relation? Can you find? Tejas, you have already answered this question. Thank you. I think Tejas had already answered this question. Others, guys, try to answer now. So, what is the radius of this bigger sphere in terms of smaller sphere? Uh, yes, cube root in. Okay, then Shaudu, correct. That's the answer. So, from here, guys, if I want to solve 4 by 3 pi, 4 by 3 pi will cancel. So, what's remaining with me? What's remaining with me? I get r cube is equals to n times of small r cube, right? You just cancel, you just cancel. So in what will be I pending with r cube is equals to n times of small r cube. From here, if I want to solve for r will be cube root of n r cube. So this will be n power 1 by 3 r cube, right? Hope everyone got this. So, so again, guys, see, correct Hari Prasad, superb. So again, see guys here, these small n number of charges all come accumulated on the surface of the bigger sphere. So what is the net charge, guys? What can you say about the charge? What can you say about the charge? Charge. So n number of small q combine to form a charge of big Q. If I call this as big Q, if the charge on this bigger sphere is big Q, capital Q, then n number of small q's combine together to form big Q. Can I write this? Yes, yes or no? Yes, n number of small q's combine to form bigger Q, right? Now, now, write the expression for potential, guys. Potential of large drop. So what do you think the expression for potential is? Electric potential is given by, what is the expression for electric potential, guys? Yes, correct, Ramakrishna. Madhavi, I didn't understand what you are trying to say. Yes, correct, Madhavi. Okay. So the potential drop, or potential on bigger drop is potential of big drop. Here, is equals to, yes. So in terms of shape, you say I have a bigger drop of charge Q with radius R. What is the potential on this bigger drop, guys? Yes, Tejas, correct. General form, yeah, correct, Hari Prasad. So V is equals to K Q by capital R, right? Or V big is equals to K Q by capital R. Now, guys, try to substitute all the values. Do you know Q? You know Q. Do you know R? Yes, you know R, the value of R. This is value of R. So if you substitute in this, what will you get? What will you get if you substitute all the values of this in this equation? R equation is wrong. Oh, okay. Thanks. Okay, this is the equation, guys. So I wrote R cube also. Thanks, Madhavi. Yeah, corrected Devikarani. Thank you. So what is the potential at bigger charge, guys? V big equals to, try to substitute everything, all the values, n times of small q divided by n times of 1 by 3 into small r. Okay, I substituted this. Try to simplify this, guys. What's the expression you get? Someone reply in the chat. V big in terms of V small. Yes, correct, Ramakrishna. Ramakrishna already correct. Others, Zoom people, please try to answer. So it's k times of, yes, n cube by n by 1. Okay, I'll take this k. I'll keep k as it is. N power 1 minus 1 by 3 into q by r. So if I simplify this, I'll get v big is equals to k n power 3 minus 1 2 by 3 q by small r. So guys, we know what is k q by small r. K cube by small r, this one. Yes, v small. So n power 2 by 3 times v small. So this is the relation which we get for this. Okay, guys, hope everyone have understood this question. Everyone have understood this question? Yes. Awesome, guys. Cool. So, Artha, any confusions at any point in this question? So, we have one question, the previous part, and that is the, yeah. Okay, this question will continue later. But this question, I hope everyone have understood this. Yes? Guys, I hope everyone have understood this. Please reply all steps. If you have understood all steps, please reply. If you have any doubt, please let me know. Yes. Sumar sati keltin enta. Okay. Tala keduskobidi. It's just once. Yes. Okay, guys. So quick summary. So what we learned. Okay, what we learned in this electric potential. So tell me what you learned in electric potential so far. So we started with work done. So we started with first thing is work done. External work done was is equals to FE F external times D. That was nothing but W external is equals to K Q1 Q2 into 1 by R2 minus 1 by R1. This was the first expression which we learned. Next we started with since this was a conservative force, F external was a conservative force, we equated the work external as change in potential energy, that is UB minus UA, right? Then we learned electric potential V is equals to the change in potential energy per unit charge, right? The change in potential energy per unit charge. This is nothing but W external by Q. This was also equal to this. Next, guys, yes. So next we learned about relation between electric field and potential. So the relation goes like this. E is equals to minus dV by dr, or E dot dr is equals to minus dV, or E cos theta equals to minus dV by dr. And what else? Integrating on both sides, we get E dot r is equals to V minus V. So these were the different forms of the same equation. Then we try to solve, yeah, next what we did, Yes, after this, we tried to solve some problems based on these, and I think this was most of it, right? Did we miss anything? Did we miss anything anywhere? So, yep. So this was electric potential to you guys. Then, yeah. Okay, last one. Right, I missed this. So lastly, we studied about equipotential surfaces. That's it. So what is equipotential surface, guys? These are always perpendicular to electric field, perpendicular to electric field. So V is constant at theta is equals to 90 degree. When we go at theta equals to 90 degree, the V is constant, and these constant surfaces where we join the locus of points, we get a plane. This plane or surface is called as equipotential surface one. Then what else? Yeah, this was much of it. When theta was 0 degree, this was maximum, right? The electric field experience was maximum and the potential was negative. So these were the several conditions, and we learned that in the direction of electric field, what happens in the direction of electric field? Guys, reply in the direction of electric field. Fill in the blanks. The potential drops. Yes, potential drops. Is that the only thing? One more condition. Potential drops fastest. Yes, the potential in the direction of electric field, the potential drops fastest. Okay, that was the one condition which we had studied in relation between electric field and electric potential. Okay, guys. So hope everyone is clear with electric potential. Yes. Click on as. Yeah, we have one pending question. Please try to solve that. I'll try to solve in a common way and share that answer in your notes. In today's notes only, I'll share that. Okay. Okay, guys. So let's go to next topic. So we'll be starting with the next topic, that is electric dipole. Okay. So we'll be starting with electric dipole. So guys, tell me, what is a dipole? What do you mean by a dipole? Yes, correct, Ramakrishna. So Ramakrishna, Namrata, yeah, everyone, it's correct. But the answer is the potential decreases fastest. Okay, you have to consider that condition also. The potential decreases correct, and but it decreases the fastest. Okay. Okay, guys. Now tell me the next topic. So what is a dipole? What do you mean by a dipole? What is a dipole, or what do you mean by a dipole? What happens inside a dipole, or what is a dipole? Okay, in today's class, we'll be talking about dipoles. How are they formed? What are different types of dipoles, and what is the electric field due to a dipole? Okay, so let us start with a quick recall test, guys. Everyone, try to take the test. So I have, yes, correct, Namrata. Correct, Madhavi. Correct, Radhakrishna. Hari Prasad. Yes, dipole is same charge between two. Yes, same magnitude of charge but different in sign. Okay. So everyone, I have launched a poll for everyone in Zoom. Others, please try to answer in chat box. Like all the YouTube live people could answer in chat box. All Zoom people could answer in your polls. Yes, correct, Ramakrishna Reddy. Superb. Yes, correct, Bhargava. That is a dipole. Exactly. So yeah, guys, come on. So hope everyone is trying to solve, and there are 20 plus students here in Zoom. Please try to solve. So angle between equipotential surface and the direction of electric field is, yes, just now we discussed that. Okay, so I'm going to end the poll, guys. Yes, the correct answer is option B. Yes, most of you have given the, I mean, all of you have given the correct answer. Answer is option B, that is 90 degree. Second question, guys. Second question, try to solve this. I mean, try to answer this. I want more people to answer. Try to participate. Yes, correct Namrata, correct Bhargav, correct Lakshmi. Potential energy due to a system of two negative charges. Yes. So we have a system of two negative charges. So what is the potential due to these two negative charges? So guys, just remember. Yes, correct. Just remember the formula of potential. What is the formula of potential? Formula for potential is V is equals to K Q by R. But here they are asking potential energy. Remember, its potential energy U is equals to K Q square by R. K Q1 into Q2 by R. Say I have two negative charges, guys. What's the force? I have two negative charges. What's the force between them? Yes, correct. Hari Prasad, correct. Ramakrishna Reddy, correct. Namrata. Others, guys, try to solve, try to answer. YouTubers, yes, yes, Arun, correct. So if it's so, which kind of uh, electric potential energy do you experience, Arun? Arun, your answer is correct, but which type of force or which type of potential energy do we get? Okay, so I'm going to end the poll, guys. Yes, most of you had given right answer. I mean, most of you have equally given the wrong answer too. So answer is yes, it's positive, guys. Why? So we know the change in potential energy U is nothing but, or potential energy in general U is K times of Q into Q by R, right? So here, if we have system of two negative charges, say minus of minus is a plus, right? It's always a positive charge. So yes, potential energy due to a system of two negative charges is always positive. Next, the question is electric potential is a quantity. What type of quantity? So guys, does anyone know? Okay, what is a tensor quantity, guys? So we'll learn the important thing. So we know scalar, we know vector. What is a tensor? Curious question. Like, I have a curious question. What is a tensor? Yes. Prakash, not exactly. Prakash Koda, exactly hangala. Pseudo vector is something different. Pseudo vector is more like current. Current has a magnitude and direction, but it's not a vector. That's a pseudo vector. Prakash. Why current is not a vector? Because it does not satisfy the vector law of additions. So current is not a vector quantity. Hence, it's called as a pseudo vector. So what's a tensor then, guys? And this is one important. I mean, this is a question. So tensor quantity. No, Madhavi. Okay, I try to answer this question. It's enough, guys. Electric potential is a dash quantity. So I'll tell you what is a tensor. Okay. Yes, correct, Lakshmi. Correct, Ramakrishna Reddy. Correct. Okay, guys. So I'm going to end this poll too. So let's check what's the answer. Okay. So the answer is it's a scalar quantity. Yes, electric potential is a scalar quantity, and it's added algebraically. So what's a tensor, guys? Now, what's a tensor? Tensor is nothing but it's a form. It's a kind of scalar and a vector. Yes, correct, Mega. It's kind of a scalar and a vector. So most probably it's a vector quantity. It's a vector with two directions. So usually vector has only one direction, right? So a tensor is a quantity which was given by Einstein. So Albert Einstein gave this in his theory of relativity. So according to him, a tensor quantity is a one which is kind of a vector with two directions. It has magnitude Yes, it has a magnitude, but it has two directions instead of one. So that's a tensor, guys. So for your information. Yep. Next, yeah. Himanu, I think current, electric current does not satisfy vector addition. Yes, correct, Hari Prasad. Tensor means having direction, magnitude, and a plane. It has two directions. A plane has two directions. So yeah, that's it. Devikarani, to an extent, it's correct. Okay, next question, guys. The electric potential at center of a metallic conductor sphere is. Yes, guys, come on, try to answer this. So, guys, you have to answer this question. It's very important. So, to answer this question, you should not remember the electric field inside a conductor. You should remember what happens. So, yeah, you should remember that exactly electric field inside a conductor. And what was the condition we gave for equipotential surfaces? In equipotential surfaces, what was the condition we studied for a conductor? So, most of you are wrong. So, try to answer this question. I'm launching the poll. So guys, yeah, you have to revise a bit, okay? So I see most of you are not revising. You should revise at least once. Take a glance of the book. I mean, what is being taught. Yeah, I think you could answer most of the questions then. So I'll share the concept only. So only one person had given me the right answer so far. Yes, Dhanush, correct. No Bhargav, no Hima, no Lakshmi, no Prajwal. So only one person gave me the right answer so far. Okay, two more. No Prajwal. ನೆನಪಿಸ್ಕೊಳ್ಳಿ, try to remember, guys. ಅವತ್ತು, like when we were studying the electric field passing through a conductor, what did we study? Try to remember. No Namrata, no Tejas. What did we try? What did you guys understand? So we try to learn the electric potential for when passing through a conductor. So equipotential surfaces in conductor through conductor. If you try to remember that, you'll get. Yes, Namrata. Correct. So I'm going to end the poll, guys. Yes, others try to answer. I'm waiting for more answers. Okay, whoever gave the answer right now in the poll is correct. So I'm going to end the poll, guys. So cool. So guys, tell me one thing. So I have received lots of wrong answer, though. Okay, so try, guys. Tell me one thing. No, no Madhavi. So I had, guys. Do you remember this? I had a conductor. I had my electric field lines passing through the conductor. So what happens to the E net inside the conductor? Net electric field inside the conductor. Net electric field inside a conductor was equals to, what was the net electric field inside a conductor, guys? Yes, net electric field was equals to 0. So again, come on, tell me this. So in a uniform electric field, if I considered a surface by moving 90 degrees or perpendicular to the electric field, what we got? What we got? What did we get in this case? So when we try to move perpendicular to the electric field in a uniform electric field, when we try to move in the particular direction, we got something. So what we got? We got equipotential surface, right? So what is the change in potential in equipotential surface? Delta V. Yes, we got equipotential surface. Correct, guys. So what was delta V in this case? What was delta V in this case? The change in potential. Yes, correct. Correct, Bhargava. Bhargav Ratnala, your answer is correct. Yes, it was okay. Hariprasad, yes, correct. Dhanush, yes, correct. Hold on. So my the change in potential of this equipotential surface was 0. Then what did we say? What did we say about the potential throughout the surface, guys? What did we say about the potential throughout the surface? Here we go. What did it say about the potential throughout the surface? Constant or equal, right? Now, instead of this metal conductor, I'll replace this metal conductor with a metal sphere. Metal sphere. I'll replace this metal conductor with a metal sphere. What happens in this case? What happens in this case? What happens to E net? E net will again be equals to 0. So when E net was equal to 0, we concluded one thing. What was that? The potential at all points of this conductor should be what? For V equals to 0, or so for delta V equals to 0, the potential at all points of this conductor should be constant. Then which should be the answer? Guys, please try to revise, okay? So the answer is option C. Yes. Yeah. When an electric field is passing through a conductor, the net electric field inside a conductor is 0. So we consider the potential at all points of the conductor is constant. Okay, the potential at all points of the conductor is constant. So we get a equipotential surface inside on the surface of the conductors. Similarly, here we have given a metallic conducting sphere. Yeah, we have given a metallic conducting sphere whose potential at all points when an electric field is passing through it, whose potential at all points remains the same. So equal from potential at surface of the sphere. So the electric potential remains the same throughout that conducting sphere. Okay, I hope you have got this, guys. I hope everyone have got these questions. Any doubts so far? Any doubts so far? Any doubts in any of the questions? Please click on yes or no. If you have doubts, click on yes. If you have no doubts, click on no. Please help me. Yep, thank you. So, guys, now we'll go to the electric dipole introduction. Okay, let's start with dipole, guys. So, guys, do you remember this? Do you remember this? What is this? Do you remember quantization of charge? Waiting for response. Yes. So what is quantization of charge? That was nothing but Q is equal to plus or minus NE. What does this mean? What did this mean? What did this Q is equal to plus or minus NE mean? So what did Q is equal to plus or minus NE means? Okay, this was quantization of charge which we studied, right? This means whenever we are trying to, yeah, whenever we are trying to remove a charge or add a charge, whenever we are trying to remove a charge or add a charge, or in charge transfer, always the charge is transferred as an integral multiple of n, right? My charge is always transferred as an integral multiple of n, where n is the integer and e is an elementary charge. This was quantization of charge which we studied, right? Yes, correct, Namrata. Yes, this was the basic idea which we studied. But I have shocking news for you. Yes, correct. Yes, correct, Hari Prasad. So this property of charges is not followed in certain cases. Okay, so there are certain cases where we cannot apply this property of quantization. Okay, so this property cannot be applied in certain cases. Those cases are: one, in the case of an electric dipole; two, in the case of a continuous charge distribution. Sir, how, sir? How can't we? Guys, you know dipole? How is then dipole formed? Let's have a discussion, guys. Try to help me, or try to give me some idea of dipole. How can we find a dipole? An electric dipole, okay? Not about magnetic dipole. Yeah, we can find magnetic dipole everywhere, but how can we find an electric dipole? Is electric dipole originating in universe? Is it original? Is it a real one? Is my electric dipole a real one? Yes, right. So can you give me examples of dipole, guys? Electric dipoles. Okay, charge is quantitative. Charge of a conductor. Okay. Okay. Distance between two point. Okay, molecules. What type of molecules, Dhanush? What molecules? Yes, Dhanush. You have raised your hand. Please ask your doubt if you have any. Yes, correct, Dhanush. Yes, cool, cool, correct. Ionic compounds and all others, right? Dhanush, you have raised your hand. If you have any doubts, please ask me. Okay. Yes, that's correct, Dhanush. Cool. Then we'll study about electric dipole. So what we do, we'll consider an hydrochloric acid. Okay, you know HCl molecule, right? So you know HCl molecule, guys. So to study a dipole, we'll consider this example. Is HCl a dipole, guys? Is HCl a dipole? Yes. So let us consider an hydrogen atom. Okay. So let us consider an hydrogen atom. What is the valence of this hydrogen atom? What is the valence of this hydrogen atom, guys? One. Right. Now let us consider chlorine atom. What is the valence of this chlorine atom, guys? I hope everyone knows what's valence. Hope everyone knows what's valence. Valence means the amount. I mean, it's the outermost, the electron, the number of electrons in the outermost orbital. If I'm wrong, please correct me. I think this should be valency. Valency, right? So valency is one for hydrogen, and valency is again. What is the valency of HCl? Again, here also valency is one. Number of valence electrons available is how many number of valence electrons are available here? Seven, correct. So I hope I'm correct with the terminations of chemistry. Valency for hydrogen atom is one, and valence electrons is one. Valency of fluorine atom is one, and valence electrons is seven. I hope I'm correct. Yes. Now, if I consider a hydrogen molecule and sorry, hydrogen atom and a chlorine atom, and if I want to form if I want to form hydrochloric acid molecule, which type of bond would it form, guys? If I want to add these two, which type of bond should it form? Reply, Madi. Which type of bond should it form? Oda. Okay. So guys, is it an ionic bond or an electrostatic bond? Is it an ionic bond or electrostatic bond? I'm having no idea of yeah, chemistry. Please try to help me now. Okay, both are same. Okay, cool. So is it an that's what I'm asking. Is it an ionic bond or a covalent bond? Okay, some bond. Okay, there exists some bond between the hydrogen atom and a chlorine atom. Now, what happens is my hydrogen atom shares one electron to this. I mean, the one valence electron which was with it, it will share to a chlorine atom, and it will also take one. Yeah, it will also take one electron from the chlorine. So now, if we see the hydrogen atom in its outermost shell, it has two electrons. Similarly, the chlorine atom also has in its outermost shell it has eight electrons. So it have both have reached their octet structure. I think that's octet structure. Please help me learn this, guys, or help me if correct me if I'm wrong. Okay. That is called as octet structure. Now, what happens is, see what's happening here in this case. My hydrogen has donated one electron to chlorine and gains what charge? My hydrogen, when it donates an electron, it gains a partial positive charge, del positive charge on it. And my chlorine, which is electrophilic, I think it's yeah attractive in nature, right? It attracts electrons towards itself. It's having higher affinity for electrons. Okay, in general terms, it has more love towards electrons, so it will pull all electrons towards itself. Is it? Yes. So since it has more number of electrons, it gains a partial negative charge. Okay, so what happens this, okay, when it takes or when it accepts an electron, and when it donates, when the hydrogen atom donates an electron and when the chlorine atom accepts an electron, what happens? There exists a dipole, right? In this case, the electron shared between hydrogen and chlorine are a bit closer to chlorine. Is that right, guys? Hydrogen shared with hydrogen and chlorine. If you see this electron which is shared, this electron is much more closer to chlorine than hydrogen. Howda? So this creates a partial positive charge on one end, a partial negative charge on the other end. Yes, it's a covalent bond. Yes. So since this is a, okay, I hope this is a covalent bond. Uh, yeah, not electrostatic bond. It's a covalent bond because I remember sharing is caring is for covalent bond. Am I correct? Sharing is caring was for covalent bond, right? Yes, cool. Thank you. So now, yeah, there exists a covalent bond, and what happened? It shared one electron. It donated, or it they both agreed to share one electron. So hydrogen shared one electron, chlorine shared an electron. Now both hydrogen and chlorine both have two electrons in, or hydrogen has two electrons in its outer shell, and chlorine has eight electrons in its outer shell. Now this electron which was shared with the chlorine is slightly towards the chlorine than hydrogen. So can I say chlorine is electrophilic in nature, which attracts the electron towards itself. So it gains a partial positive charge, and since my hydrogen donated an electron, it gains a it gained a partial positive charge for hydrogen and gained a partial negative charge for chlorine. Now, this slight positive charge and negative charge, this slight positive charge, the del positive and del negative, are the slight charges whose magnitude, the magnitude of these charges is less than that of a charge, is less than that of the magnitude of a charge, right? What was the magnitude of a charge, guys? It was 1.6 into 10 power minus 19 coulombs. So this charge, which is formed on the hydrogen atom and the chlorine atom, is partially, it's a partial charge, which is much lesser than that of a magnitude of actual charge. So here, in this case, the electric dipole, okay, the electric dipole form does not satisfy the quantization of charges property. Magnitude of del plus and del minus on H atom and chlorine atom respectively is less than the magnitude of the charge. Okay, so this is the condition. I think phobic, Hari Prasad, I think phobic means fear, philic means love. So yeah, it attracts, philic means it attracts more electrons. I guess that's the right answer. Yes. That's correct, Hari Prasad. Yeah. So, guys, similarly, how is charge distribution continuous? Okay, how is it in continuous charge distribution? The quantization of charge is not satisfied. Let's see. In case of continuous charge distribution, what happens? Okay, thank you, Namrata. So, in case of continuous charge distribution, what happens? So, so I have given you several cases, guys. So, in case of continuous charge distribution, say if this is a linear charge distribution, say I have different types of charge distribution: a point charge distribution, a linear charge distribution, a surface charge distribution, and a volume charge distribution. So in all these cases, what's happening when I give a charge to this point charge? Yes, the point charge accumulates the charge. When I give a number of charges to this linear charge, I assume, what do I assume? I assume all my charges are distributed throughout the body evenly or uniformly. So all charges are distributed uniformly. Okay. I consider this, I assume this is a case for a surface charge or even for a volume charge. Now, when we have when we have provided the uniform charge distribution, what happens? This charge is not discrete. Can we say, so I have provided 10 charge, means say I have some 100 n amount of charges and I start to distribute it, and it distributes evenly all over this surface of linear charge, all over the surface of surface charge, and all over the volumetric outer surface of this shape. Now, don't consider the charge distribution to be discrete or quantized. So what is discrete or quantized means, guys? What is discrete or quantized means? What do you think discrete or quantized means? We can't give an exact integer value for this. This discrete means or quantized means we cannot give, we can't give exact integer value. Okay, we can't give exact integer value at a given position. So in a continuous charge distribution case, we cannot give a discrete value of charge on particular space, since it's distributed all over the region. Okay, so even in this case, the quantization of charge will not be considered. Okay, instead we assume the charge is continuously distributed throughout. So in these two cases, my quantization of charge will not be applied. The property of quantization of charge is not applied. Next, so we are going to study about these special cases of yeah, these two are special case, right, for us. When this is not satisfying a property, these two are special cases. The one is dipole and the other is continuous charge distribution. So we'll be studying about them. So we'll be studying about electric dipole, field due to electric dipole, and potential due to electric dipole. Dipole in an electric field, continuous charge distribution, electric field potential due to linear surface and volume charge distributions. Then we'll study two cases of linear conductor and a ring, where we would find the electric field and electric potential for those specific cases. Okay, so let's start with the structure of dipole. Guys, how do you think a dipole looks like? So how do you think a dipole looks like? Come on, guys, reply please. Reply please. A dipole, yeah, guys, listen. A dipole consists of two charges of same magnitude. So we should consider two charges of same magnitude, but opposite in signs. Okay. So how to construct, or what is the structure of a dipole? We should consider two charges of same magnitude and opposite in charge. Okay, opposite signs in the charge, or opposite signs of charge. Now, if these two dipoles are separated by a fixed distance of 2a, so what we have, what is the other condition? The third condition is these two dipoles, these two point charges which are oppositely charged with same magnitude should be separated by a distance of 2a. Then, if C is the midpoint of these two dipoles, if C is the midpoint of these two dipoles, then we could say the dipole, the line joining the charges is called as axis. Then this will be considered as the structure of a dipole. So this is the structure of dipole, guys. So what happens? A dipole consists of a positive charge and a negative charge of same magnitude separated by a fixed distance. This distance is fixed, separated by a fixed distance, and the line joining these two charges is considered as the axis of the dipole. Okay, so this is the structure of a dipole. And in physics, we have one particular thing. So each dipole will be having a particular direction called as the dipole moment. This is called as the dipole moment, or direction. Each dipole will be having a particular direction, and the dipole in physics, we will be considering the dipole direction or dipole moment direction in physics is from a negative charge to a positive charge. Okay, so I have mentioned all the nodes, which I have mentioned all the points here. So there are two charges of same magnitude but different in sign. The two charges are fixed by a fixed displacement or a constant displacement of 2a, where C is the midpoint of the charges. The line joining these two charges is called as the axis of the dipole, and the direction of the dipole movement is from negative charge to positive charge always in physics. Okay, guys. Guys, this is yeah. So it's a yeah, it's general the electrostatic force, Hari Prasad. Yeah, we have made it to separate. We have made it to sit separately by a distance of 2a. That is how we it works. Hari Prasad, hope you I answered your doubts. Okay. So dipole moment. The dipole moment exists between two charged bodies due to the difference in charge density. So we studied this, guys. So we studied in an HCl molecule what was happening. The chlorine had affinity to pull all the electrons towards itself. So it had partial negative charge, and the hydrogen had a partial positive charge, right? Due to this difference in charge densities, what happened due to this difference in electron density? There exists a dipole moment. Okay, the dipole moment is now given as a product of magnitude of one of the charge. Say, how is dipole moment given? The dipole moment is given as the product of magnitude of a charge times the displacement vector 2a. Okay, this direction, the direction of dipole is always from minus q to plus q. Okay, guys, click on yes if you have understood this. This is basic properties or basic construction or structure of dipole. Hope you guys have understood this. Yes? Okay, cool. Thank you guys. Thanks for the response. Now, dipole moment is considered as a vector quantity. Okay. The dipole moment is considered as a vector quantity whose magnitude is given by the magnitude of dipole is given by P is equals to Q times of 2A, and the direction of the dipole moment is along the direction from minus Q to plus Q. This we had discussed already. I have given it in the notes. Yes. The SI unit of dipole is, what is this, guys? The SI unit of dipole moment. SI unit of dipole moment is coulomb meter. Please make a note of it. It's coulomb meter, not centimeter. Guys, always centimeter is small c. This is coulomb meter, capital C M. Okay. The dipole moment is given by SI unit coulomb meter. Okay. So this is the basics of dipole and its structure and dipole moment. So there is a significant difference between physics and chemistry. So dipole moment direction in physics is from minus q to plus q, and dipole moment exists between charges or charged bodies. So in case of dipole moment in chemistry, what happens is the dipole moment in chemistry is opposite to physics. So dipole moment exists from plus q to minus q in chemistry, and it's because of movement of electrons or shift of electron density from electrophobic to an electrophilic atom in a molecule. Okay, guys. So if you have got that, please try to answer this question. Guys, try to answer this question. Okay, why dipole moment magnitude is not negative? What is dipole? Okay, why is it not? P is equals to Q times of 2A, right? So if you have a negative charge, okay. See, we are considering a positive and negative charge, right? So dipole moment. What is a moment, Hari Prasad? What is a moment in physics, which we had learned in our 11th? If you know that what is a moment, then you could answer this dipole moment. Okay, what's a moment? So moment means it's the force involved in a motion, right? Similarly, dipole moment means it's a sort of energy. Okay, it's a sort of energy associated with the two dipoles. So we have considered only the positive magnitude. So energy can never be negative in magnitude. So we have considered the positive magnitude of the dipole. Okay. So it's the dipole moment magnitude is always positive. So even if we have a negative, see, even if there is a negative thing, it only associates is the negative sign symbolizes only the direction. Okay, anywhere in physics, the negative direction except for the scalar quantities. Anywhere, whenever we have a vector quantity, yes, whenever we have a vector quantity, in all cases my vector quantity, whenever I have a negative sign, it means the opposite direction only. Hari Prasad. Okay. Okay, correct guys. Cool. All of you have got, I mean, most of you have got this right answer. So HCl molecule has a dipole moment of magnitude 3.4 into 10 power minus 30 coulomb meter. So this is 10 power minus 30 coulomb meter. Assuming that equal and opposite charges lie on the two atoms to form a dipole, what is the magnitude of charge given the separation between the two atoms is 1 into 10 power minus 10 meters. Yes, guys, correct. Tejas, Prajwal, Shashwata, correct. Bhargav Ratnala, correct. Yes, guys, most of you have got the right answer. So we'll try to solve this question, okay? So what's given? An HCl molecule has a dipole moment. So P is given to us. P is equals to 3.4 into 10 power minus 30 coulomb meter. Yes, correct, Devikarani. So the separation between them, the separation between the two atoms is given as, say, 2A. Okay, 2A is equals to 1 into 10 power minus 10 meters. Now find the Q. Apply in the formula. What is Q? So we know that P is equals to Q times of 2A. So 3.4 into 10 power minus 30 is equals to Q by 2 times of A is 1 into 10 power minus 10. So if you try to solve this, you'll get, yes. So all are in meters only, right? So it's 3.4 into 10 power minus 3 into 10 power. What happened? Guys, I think there is 3 power minus 30, right? Yes, 30. Okay, this is minus 30 plus 10. So 3.4 into 10 power minus 20 coulombs. Okay, yeah, got it, Mega. Thanks for the answer. So option A is the correct answer. Cool, guys. Then I will continue the remaining part. Please try to revise. Please try to study in your homes. Please try to revise again the concepts which we had taught so far, which we had learned. So in today's class, we learned about dipoles. So the quantization of charge was not satisfied. The quantization of charge property was not satisfied by two conditions. One is dipole, other is continuous charge distribution. So we will be studying about both the cases. So we saw examples of two cases. So in first example, we saw the hydrogen hydrochloric acid molecule, which was a dipole. So what was happening in that? So hydrogen donated one electron to chlorine, and chlorine accepted that electron. I mean, there was a covalent bond formed, and this electron which was donated was partially, I mean, yeah, was more electrophilic. I mean, since chlorine was electrophilic, it attracted electron towards itself. So it was bit away from the hydrogen, closer to chlorine, more closer to chlorine. So there was a difference in the electron density between the two atoms. So there exists a dipole, and there existed a partial positive charge on hydrogen atom, and existed a partial negative charge on chlorine atom. So this created a dipole. Okay, with partial positive and negative charges. This partial positive and negative charges now had given rise to a dipole moment of P, that is equals to Q times of 2A. So that's how we got a dipole. Similarly, in case of continuous charge distribution, what happened is when we provide some amount of charges to any system, so, to any body, we assume that all the charges are equally distributed on the surface of the body or on the outer surface of the body. Yes. So this assumption, okay, this thing which we see, the distribution of charges, we cannot say the exact number of charge at any one single place. Say if we have continuous charge distribution over here, say in case of surface or linear charge in a linear conductor or in a surface conductor or in a volumetric conductor, what happens, we if I select any arbitrary point, say if I select any arbitrary point, I cannot give an exact discrete value of charge over this point, because these charges are continuously moving, or yeah, these charges are not stagnant, not stationary, they will be moving, and yeah, they're distributed throughout, so I can't give an exact discrete data about how much charge is present at a particular point in a surface. So we assume that it's all the charges are continuously distributed. Then we started with dipole. The structure of dipole. The dipole consists of two positive charges. Two charges with equal magnitude but opposite in charge or opposite sign, separated by a constant fixed distance of 2a. And this the line joining the two charges is called as axis, and there exists a dipole moment in physics, which we consider the dipole moment from a negative charge to a positive charge, whereas yeah, the dipole moment is given by P is equals to Q times of 2a, and dipole moment is a vector quantity, okay, whose magnitude is Q. P is equals to Q into 2a, and direction is along plus minus Q to plus Q for physics, and its SI unit is coulomb meter. Then we studied how the dipole moment varies in physics and chemistry. In chemistry, the dipole moment is opposite in direction and represents the dipole moment represents, say if I have a minus q here and plus q here, then my dipole moment is from here to here, because this represents the movement of electron from a higher, I mean, from a region where, from an electrophobic atom to an electrophilic atom, right? So dipole moment represents the movement of electrons or shift of electron density towards more electrophilic atom in chemistry. Okay, this dipole moment represents that. Okay, then we solved a problem based on that, and yeah. So we'll try to solve more problems, and we'll discuss about polar and non-polar dipoles and other properties of dipoles. We'll derive an expression for electric field due to a dipole and electric potential due to a dipole in our next class. Please come prepared to the next class, guys. And thank you. Yes, guys. So cool. Okay, people at YouTube, thank you for being here. We'll meet again in next class.